Hi, welcome to Chem 6161. Today we will talk about Chern-like transition states. We will study these three reactions. The reduction of one free ketoalcohols with this diethyl boron methoxide. Okay, this is a Lewis acid, plus the use as a reductant of sodium borohydride. We will reduce this ketone to get the syn diol. In the second case, we will study again the reduction of one free ketoalcohols. Okay, this time with this triacetate borohydride, and what we will get in this, using this method, is the anti-substitution. And at the end, what we will see is the alkylation of beta hydroxyesters, okay, or one free hydroxyesters, using two equivalents of LDA. Remember that the first equivalent will be to eliminate, to take the hydrogen of the alcohol, and in this case we will get the anti-alkylation. Okay? This is what we will study today. We will start for the first example, for the first reaction, okay? This one. And we will go step by step. When we are treating a ketoalcohol, one free ketoalcohol, with these reagents, this diethyl boron methoxide and sodium borohydride, the first thing is that we will have the coordination of the ketoalcohol with the Lewis acid, this boron compound, and what we will have in first step is the formation of this intermediate. And as you can see here, this is a 1, 2, 3, 4, 5, 6 member ring. The next thing that we need to decide is which is the conformation with lower energy of this compound. In order to do this, basically what we need to do is to draw the half chain. How we draw the half chain? Okay, we put our eye here, okay, and we can get two different chairs. If I put the eye here, the first that I saw is the double bond. Always the double bond has to be here. In this case, the double bond is corresponding to the carbonyl. And then, in the direction up, that means in this direction, what we have is the boron. Okay, and in this direction, what I have is carbon number 4. Always is good that you put the numbers in order to don't get lost. Then, I am in carbon number 4. I have to draw carbon number 5. I have two options. I can go up or I can go down. I will go up, okay? And here I will draw exactly the same, but going down. Okay? This will be the two half chairs conformation of this compound. Okay? Next, I put the oxygen. If this is going down, the oxygen will go up, will go down, and I close the cycle. In this case, the oxygen will go up, and I close the cycle. I put this a little bit there. I draw the two possible chairs. Next step, I put the substituents. Okay, in the boron it's very easy. I put two ethyls, I don't care where are. Okay, next one, I have to go to carbon number 5. And if in carbon number 5, if the oxygen is down, the hydrogen will be up, and R1 will be in the equatorial position. While here, if I draw it, R1 will be axial and the hydrogen will be equatorial. And now what I have to decide is which is the most stable conformation. In this case, because R1 is equatorial in this case, the equilibria will be to this compound. This is the most stable. Okay? It's quite easy. I draw both half chairs and then I analyze which will be more stable. Obviously will be this, because R1 is in the most stable conformation. I'm sorry, I forgot to here write R2. Okay, but R2 basically is coming to us. It's not important because it's perpendicular to the plane of the slide. Okay? Then this is the most stable. I can't forget this one. I will erase this one. Okay, now we have this compound, and what we need to analyze is the trajectory of the nucleophile, in this case the hydrogen. Okay, the nucleophile can come from up, following a Burgin-Dunitz trajectory, and will be more or less like this, or by down, and will follow like this. Okay, the Burgin-Dunitz trajectory, that will be more or less in this direction. Okay, then what's next? We have to analyze the trajectory. Seems quite okay that the nucleophile, when it's coming from up, okay, is crashing with these two substituents, isn't it, that are also up. And the nucleophile, when it's coming from below, seems that it's quite a straight way. It's quite a straight that will attack the carbon. The carbon. If we only check this, probably you have to decide that the nucleophile will come from behind. However, we will draw the transition state. Okay? The transition state for the right approach will be that we have, I draw exactly the same that I have before, double bond, boron, okay? And if I do this and the nucleophile attack this position, I will draw the rest of substituents, okay? What will happen is that the hydrogen will come here, okay? The nucleophile, you can put whatever you want. This oxygen, because remember, it's sp3, will come a little bit down. And what we will form is more or less we will get this intermediate. Okay? If this is pushing here, the oxygen will come a little bit down, and we will form with a very good phase a chair-like. Okay? While if we do the other, what we will get, okay, if the nucleophile attack from below, what we will get is, I draw exactly the same than before, okay, but now I will have the hydrogen more or less in this direction. That means that this will come up, the oxygen, and this R will come, R2 will come here, R1 and I. And I will have like a twisted bolt. If we analyze these two transition states, which will be more stable? This one that is like a twisted boat, or this one that is a chair-like? Obviously the chair-like will be more stable. Remember that the most stable conformation for a six-member ring, sp3 of his carbon, will be a chair-like, a chair. Okay, a chair conformation. That means this transition state will be more stable, and this is the reason why the nucleophile attacks from up, from the upper position, and not from behind. That means that this will be the right transition state, and then if I draw it, what I will have if I translate the information after hydrolysis, I will get the syn diol. In the case that I draw, because the nucleophile is a hydride, what I will get is this compound, the syn diol. Okay? Right? These are the three steps. First, we draw the complex with the boron. We draw the most stable child-like transition state, okay? Child-like intermediate, sorry. That has to be the one that has the substituent in axial position. Next one, I draw the approach of the nucleophile once it's going to the carbonyl group, and I find that when the nucleophile attacks from the upper phase, what I have is that a child-like transition state, while in the other case, I will have a twisted bolt. I choose that the most stable is the child-like transition state, and this will give the final compound. Okay? Good. This is the first example. Please at home try to draw it by yourself, and if you are not clear how to draw it, or you have problems to translate the chiral information of each carbon to the drawing, to the final drawing, or for some intermediate, please use molecular models. Okay, then we go for the second example. In the second example, the only that I change is the reagent. Instead to use a Lewis acid and a hydride, I only use a hydride. I use this type of hydride that basically is boron triacetate hydride. Okay? The reaction starts with almost the same. The wedge will coordinate with the boron, and what we have is this. Is replacing one of the acetates But now, what is the problem? That we cannot coordinate the other oxygen with the boron, because simply the boron, has a negative charge. Okay? That means that this will not work. What is happening here is that basically the hydride will attack the carbonyl. Okay? That we will activate with a hydrogen bonding with a hydrogen, with a proton. Okay? And now if we count, it's 1, 2, 3, 4, 5 plus the hydrogen 6. That means the reaction that we are doing has is like a 6-member ring. That means that we can draw it as a chair. Okay, we have 2 chairs. Okay, and we have this chair. Okay, I put the borrow here because I like it. You can put it where you want, it's not important, but I suggest here. At least for me it's easier to put it here. And I put the reference statement. Acetate, acetate. Here is coming the hydrogen. This will be something like this. Okay, then here is the oxygen. If the oxygen is here, the hydrogen is up, the substituent is in the axial position, in the equatorial position, and the H is in the higher position. And then here will be the carbonyl. And I will take later, I only draw like this, okay? And we will talk later about the carbonyl. Now we are choosing which chair is the most stable. If we do this, we have the boron here, okay, hydrogen here, we are forming this bond. Here is the carbonyl, okay, and then here is the CH4, and here we have the R1 in axial and the hydrogen in equatorial, and here has to be the oxygen. Okay? Which is more stable? Obviously, the one that has R1 in equatorial will be more stable. Right? Okay, then we can forget this chair transition state. And now we analyze the 2 positions that can be the carbon. I will draw it a little bit better, okay? At least that is easy to see. Okay, maybe a little bit exaggerated. But then I have these 2 possibilities. This with the carbonyl up, and then what I have is that the hydrogen is attacking in this way. Or I can do exactly the same. With the hydrogen, the carbonyl down, okay, and the R2 will be up, here will be the same, and now the attack will come from this phase. Okay, we have these 2 possibilities. If we analyze these 2 transition states, in this case, R2 is becoming more or less equatorial, while here R2 is becoming axial. Which will be more stable? The most stable will be this one, okay, where R2 is equatorial. That means that I will have this transition state and not this. I can delete this, and then the final product will be okay, after the reaction, this will be like this. Okay? If I translate this, I make the hydrolysis, what I will get, this center will be the same that at the beginning, and this center will be in this direction. That means that will be anti, like I said before. Okay, why we have normally lower diastereoselectivities selectivities in this example than in the example that I wrote before? Basically, because here we are checking the different conformations of this carbonyl, and the difference of energy is not very high, or that's not true. It's lower than not the other difference energy of the later example that I put. For this, normally the stereoselectivities in this case are lower. Okay? As a summary, what we do in this case, we first coordinate the hydroxy ketone with the boron, and then we grow the intermediate the transition state of the six-member ring of the hydrogenation. We choose without watching or without considering the carbonyl, we saw which share will be more stable. That will be determined by the substituents. When more substituents are in equatorial, more stable, we choose the share more stable, and then we check the two possibilities of the orientation of the carbonyl, up and down. The one that R2 looks like more in equatorial position is the one that will be more stable and will be the one that leads us to the final compound. Okay? Again, try to grow it by yourself, and if you have any problem, use molecular models. Okay. Now we will do the last one. The last one is the alkylation. Okay? How we start? First of all, we are creating this with two equivalents of LDA. That means that we will form the first equivalent will remove this hydrogen of the alcohol, that is the most acidic, and then the second one will remove the hydrogen in the alpha position. What we will get is this compound, IRO in his analyte form. Okay? And the only that I need to do is to put the lithiums that are not so innocent in this reaction. And basically, when I draw the lithium, I can do a six-member ring. The analyte with the lithium form a six-member ring. 1, 2, 3, 4, 5, 6. Okay? That means if this is forming a six-member ring, I can do exactly the same that I did in the first example. I have to study the two different chart-like transition states. How I draw it now, I watch this like I do with the boron example. I watch it in the double bond. That means that I draw here the double bond. Okay, that means here is the oxygen. The O-ethyl will be in this direction. Okay, for me it's not up or down, it's only coming outside of the slide. Here, this is 5, this is 4, here I will have 3. Okay, and then here will be the oxygen, and here will be the lithium. Okay, and I have this if the oxygen is up, then the hydrogen is in this direction and the R1 is in this direction. Okay, if I draw the same but the other chair, that means